Hello and welcome to another video by www.electricalpereview.com. In this episode, we're going to be covering an introduction to synchronous machines. Okay, the first thing we're going to tackle is our synchronous generator single-phase equivalent circuit. Most important thing is this is an electrical circuit diagram, so things you're not going to see here. You're not going to see the prime mover. You're not going to see any kind of mechanical equipment. This is an electrical diagram only. First and foremost, I just want to say expect this chapter to be really wordy. Expect it to have a lot of definitions, a lot of things you may or may not have heard before. Typically, the most important thing, just like the other chapters, make sure you can solve the math problems. Read through the definitions and concepts once or twice. Make sure you kind of understand them. As long as you can solve word problems by referencing the material, you're in good shape. So don't let that kind of demotivate you. This is going to be a long and tedious chapter. But anyways, let's jump into it. So synchronous machines are a type of rotating machine, and typically it's going to cover either a synchronous generator or a synchronous motor. So what exactly makes it a synchronous machine? Well, we've got two main components. You'll see on the left side, this is our rotor. That's the part that spins. And on this side, this is the stator. That's the stationary part. And here's our load off to the right. Essentially, you have, think of it like a backwards motor. If this was a drawing of kind of like a cut sheet of it, kind of cut in half, we would have our stator would be this section right in here. And then our rotor, I'm going to draw it solid just to make it different. The rotor spins inside the stator. So first thing we do is the rotor has a DC voltage right here. So this is our DC voltage. And what that does, it puts a current, I of X, on our rotor windings. These are the windings here in our rotor. And essentially, if our rotor is nice and long, like how it is in most synchronous generators, so if it looks something like this, there we go. And if there's a bunch of windings on it, like one big coil, hooked up to a DC power source, say plus, minus. Okay, so what that's going to do is that's going to create a magnetic field, kind of like this. That's going to make, since it's DC, the polarity of that magnetic field is not going to change. So if this is our rotor, this thing right here is going to be constantly spinning, right, inside of our stationary stator. So that magnetic field here in our rotor is symbolized by that solid circle here. Okay, so what does that do? Well, that magnetic field is going to actually induce a voltage into our stator. So this circle right here, don't let it confuse you for the shape of a stator. Remember, this is an electrical equivalent diagram. This circle right here just symbolizes the voltage in our stator, that's this guy right here, induced by the magnetic field produced by the excitation current in the rotor windings. So after that, we will have an internal synchronous reactance here. That's X of S. And essentially, remember, reactance, we're dealing with coils and magnetic fields and windings. We've got windings in our rotor. We've got windings in our stator. This is more or less the impedance, the imaginary impedance of the stator due to the coils. And that's going to produce a voltage drop. So our voltage across our stator coils is going to be here, E of X. Okay. So E of X is the voltage drop due to the stator coils, stator windings reactance. After that, we have our stator current, I, right here. And that's the current that's also all a product of our induced voltage from our rotor. So this total current in series is the actual power in amps that's going to our load. Notice here, E, this is what they sometimes refer to as the terminal voltage. Terminal voltage. It's really just another way to say if we hook up a load, if we hook up a load Z across the terminals of our generator. Kind of like that. Okay. What else can we talk about a synchronous generator? let's talk about our voltages. So our induced voltage, EO, you'll notice it's in series with our voltage drop across our synchronous reactance, and it's also in series with our load or terminal voltage, E. So an easy way to sum this up, notice the polarity of all these, right? This is going to be plus minus, and then these up here are plus minus and plus minus. So what does that mean? Well, we could sum that up as saying EO, our induced stator voltage, is equal to EX, which is the voltage drop across our synchronous reactance, plus our terminal or load voltage, E. Now, what about our current? How could we write something for our current? Well, if we start with Ohm's law says what? V equals IR. If we rewrite this for our generator components, we could say EX up here. So this is the voltage drop across our synchronous reactance is equal to the current flowing through it, which is still I, times, instead of resistance, we're going to use reactance, J, X of S. How about that? So essentially this says right here that our voltage drop from this point to this point, EX, is going to be the product of our stator current I flowing through it times this impedance value right here from that same point, which of course is our stator reactance, our synchronous reactance, X of X. There we go. Okay, what else can we say about our synchronous generator? Not pictured here, since this is an electrical diagram, but the mechanical component, our prime mover, you will oftentimes hear that, prime mover. Essentially, the prime mover is what converts the energy source, say steam, usually from burning a fuel. That's going to change, the prime mover will change the energy source to a mechanical rotational energy. Mechanical rotation. There we go. It does not want to cooperate with me today. Okay, so our prime mover essentially is going to be mechanically connected to our rotor. So if this was our electrical diagram, if we had to draw some kind of mechanical diagram, we could draw something like this. We could have one big turbine, which is kind of like just one really big fan with a lot of different blades, something like that, to where steam comes in here, hits these blades, causes the turbine to rotate, and then the turbine, we're going to draw just like a picture of a coupling. Turbine is mechanically connected to our rotor, so that as our turbine spins, so does our rotor. And we know that along this rotor is one big magnetic field. And that's because we are inducing a current into windings that are situated on the rotor itself. So really, you'll also hear the term field a lot, F-I-E-L-D. Anytime you hear field, they're referring to this magnetic field right here. Okay, so as our prime mover spins from a fuel source, it also spins our rotor. And we know that that rotor is, I'm going to pick a new color really quick. So as that rotor spins, it's spinning inside a stationary stator. Really big stator. And there's a very minor air gap between the two. So let's say that this is our stator. Not the best drawing, but hopefully it gets the point across. So this orange is going to be this right here. So this view I drew earlier, that's kind of a cross section. That would almost be if we cut that in half and we looked either that way or this way. So anyways, you also have windings in your stator. Your stator is one big coil. Think of the stator of a motor. And in that stator you have your three phase connections. We'll call them A, B, and C. And so as that, now this is a rotating field because our rotor is excited. As this rotating mechanical field induces a voltage in our stator coils, that produces power. In our stator coils, we usually have three sets. That's going to be connected to our grid. So this point right here would be our E. This is our terminal or load connection. And this right here would be our connection to our utility grid or some load if it was a smaller generator. Okay, next we are going to pick on our synchronous motor single phase equivalent circuit. If you'll notice, it looks almost exactly the same as the synchronous generator diagram, except it's backwards. Synchronous motors and synchronous generators, they're more or less the same thing, they just operate in reverse. So let's start from left to right. This time around, we have an AC power source. And since this is a single phase equivalent circuit, right, we're only depicting one phase, this is going to be our line to neutral voltage. So this is literally where we put power on our stator. So instead of producing power this way, we're now going to put power on our stator and create a magnetic field in the stator that's going to spin the rotor. So this E, if this was a 480 volt machine, this E would be equal to our line to neutral voltage. So make sure you don't let that one mix you up. Okay, next. So now we're applying the voltage on our stator, right? We have a voltage drop again, E of X, from this point to this point. That's going to be the voltage drop across our synchronous reactance, X of S. And our synchronous reactance is still the reactance or the imaginary component of the impedance of our stator coils. And now look at this. We still have a rotor inducing voltage, right? Well, the reason is on a synchronous motor, down here, on a synchronous motor, we're still inducing a voltage. So pretty much what they usually do is they will apply a voltage source on the stator, creates a rotating magnetic field in that stator. If we were to draw it again, that's our stator, and this is our rotor. And there's a very small air gap in between. This time we're creating that field on the stator, say like north, south, north, south. So these poles are going to rapidly rotate because it's an alternating current. So the magnetic field is going to rotate it as well. So as soon as you apply that voltage on those stator coils, we'll call that E, you're setting up a magnetic field. It rotates in related to the frequency of the power. Now that rotor is going to start spinning with it because the rotating poles are attracting it magnetically. And then typically once that rotor is spinning up to speed, that's when they turn on their excitation power, or VDC. And as soon as they turn that on, now we have poles created in the rotor that then instantly lock into place with the stator. So where you have an S on the stator, you'll now have an N for the rotor. And as this S pole spins, this north pole on the rotor, because the opposite poles on magnets always attract, it's going to be directly in line with it. And that's going to induce a voltage. Since we've got coils within coils, it's still going to induce a voltage in our stator. And that's still going to be EO, just like our generator value. Now let's look at the voltages. How does our voltage formula change compared to the generator? Well, let's look at it from left to right. Right off the bat, intuitively, we know that E is going to be the biggest. Why? Because that's our applied voltage. Next, we know that EO has to equal E minus this voltage drop here, because we're going to have a loss of voltage from the impedance, right, from the voltage drop. But if we just look at our voltage loop, right, our Kirchoff voltage loop, we can say, because of these polarity notations, E right here is the voltage drop from this point all the way down and back here. So E has to equal the sum of EX, our synchronous reactance voltage drop, plus EO, our induced voltage. So we can say, and this is going to be a little different than our generator, so it's not necessarily a one-size-fits-all. You always need to just look at the diagram. So this time we have E is going to equal EX plus EO. Okay. Now how about a current? What if we wanted to solve either for I, or if we wanted to solve for EX? Well, we can say that Ohm's law again is V equals to IR we rewrite it for our generator notation, motor notation. We have EX equals I times J X of S again. So this still holds true because that's simply just Ohm's law. That's just solving for the voltage drop across one impedance with the current flowing through it. So that still holds true. So this says if we know X of S and I, we can find E of X. If we know E of X and I, we can find X of S. As long as we know 2, we can find the third unknown. Just like up here, if we know 2 of these values, either E of X, or EO, we can find the third missing one. So what else? What else can we say about the motor? Well, let's draw. We drew a mechanical diagram for the generator. Let's do the same for the motor. So this time around, what's not pictured here, since it's an electrical diagram, what's not pictured here is the actual mechanical load, just how the prime mover wasn't shown in the generator diagram. So what does that look like? Well, I'm going to draw a really big stator like this. And then we've got a rotor inside of it. This time around, this rotor is going to be mechanically coupled to some kind of load. So let's pretend that this is just a coupling. And let's say we could be connected to a big fan. So a big fan would look like this. And I know I'm not the best artist around, but again, hopefully this kind of makes sense. So this time, we're applying voltage E on our stator windings. Stator windings creates a magnetic rotating field that then attracts the rotor, so the rotor spins to catch up with the stator windings. Then we put on our excitation voltage, right? Our plus, DC, minus. That locks the rotor into place, so now we have two magnetic fields magnetically coupled. And right here, since our load, our mechanical load, is physically connected to our rotor, it has to spin as the rotor spins. Does that make sense? So it's essentially a generator operating in reverse. So this is a motor. Okay, now we're going to talk about torque angle. And this is a much better diagram that I drafted to give you a better idea than my crude hand drawings. So torque angle. This could be either a generator or a motor, right? G or M. So on the outside here, this would be our stator, right? So this outside part is a stator. And then this inside part is the rotor. And then in here is a really small air gap. But anyways, when the stator, these arrows are rotating this direction, when the stator and rotor are perfectly in phase, we say that the torque angle equals 0. So if this was a generator, the rotor would be moving, the stator would be stationary, but we would have a rotating magnetic field in the rotor cutting across the conductors of the stator. If it was a motor, the stator would still be stationary, but we would be creating that rotating field in the stator and then spinning the rotor. When we apply a load to either, and when I say load for right now, I'm talking about an electrical load. When we apply a load, which would also imply that an electrical load is what? It's of course an impedance. So when we apply an electrical impedance, an electrical load, the rotor is going to fall slightly out of step with the stator. That's true for a generator or motor. If it was a generator, an electrical load would be like connecting a utility. It would be like connecting the generator to the electrical grid. So if this was the electrical grid here and we connected it at our terminal voltage point E, this would be our electrical load. For a motor, if we hooked up, say that big fan example, if we connected it to our rotor, the mechanical fan would translate into an electrical load too. So anyways, as we load up either of our synchronous machines, the rotor is going to fall back. So say for a motor, for example, the rotor is trying to keep up with the rotating magnetic fields in the stators. And just so everyone's clear, this SN notation that you see on both sides in the stator and the rotor, those are the poles of the magnetic field. So our north is attracted to our south, and our souths are attracted to our north. So notice here these arrows, the rotor is still spinning in the same direction. They're both still going to spin at synchronous speed, right, because it's a synchronous machine. But you'll notice that this angle, instead of being perfectly aligned like it was in this example, we now have an angle that it's actually out of step by. So that's this guy right here. If this was, say, our 0 point, like in the first diagram, this line right here is the amount that it's out of step. And that's where torque comes from. Now, be very careful. The alpha, lowercase alpha, is our mechanical angle. So if we were to actually get like a protractor and measure this angle, that would equal alpha. And alpha is responsible for lowercase delta, which is our electrical angle. Now, we love phasor diagrams in power. They can kind of be confusing, but they shouldn't be once you kind of get the hang of them. How would we show this actual electrical torque angle? Well, I'm going to draw a quick phasor diagram. If our applied voltage, and just for this sake I'm using a motor for example, remember the motor, we apply voltage E to the stator, line to neutral. If this was our applied voltage E, right here, and our induced stator voltage was right here, remember that's going to be our EO, and that's our induced stator voltage from our excited current in the rotor. The difference in this angle right here would be our lowercase delta. That would be our electrical torque angle. And that only works when we set E equal to an angle of 0 as reference, right? That would be no difference if it looks something like this. So if E was up here, say it was, I don't know, 25, 30, 60, something like that. If E was up here and EO was here, well, our torque angle would still be the difference of these two angles. And remember, since vectors, they're constantly rotating at all times. So anytime we draw a phasor diagram, we're looking at a snapshot. We're looking at when a time equals a specific value. So typically what we do is we always put our voltage value on the x-axis for reference, because it gives us a better intuitive standing, patterns emerge, it's easier to tell if things are leading or lagging, etc. Okay, next thing we're going to talk about is the open and short circuit test. On the left we've got a synchronous generator. You can tell because our rotor is inducing a voltage that's providing power for load. On the right we've got a synchronous motor. You can tell because we're applying a voltage to a stator, and we're spinning a mechanical load that you can't see on this diagram. So okay, open and short circuit tests, you're going to hear this quite a bit. It's important to know what they're for, why they do them, and what they can tell us. So first, open circuit, what does that mean? Well, open means that on the stator we're going to open the windings, so nothing's connected. It's kind of funny how it looks there, but okay, that's better. So the stator windings are officially open. I'm just going to draw this out in the generator, but pretty much the same applies for the motor. So open circuit test means that our windings, we don't have any kind of electrical load, they're completely open. So the open circuit says, in essence, they're measuring this voltage right here, and they're going to slowly start to increase I of x. Now say this was a 25 MVA rated generator that was rated for 13.8 kV. So the open circuit test pretty much says the excitation current is raised and it's recorded. I of x is recorded. That's going to be our IX1. This value is recorded when the voltage we measure from here to here is going to be the rated voltage of our generator here. So then they hang on to that measurement. Next, for the short circuit test, they're going to take these windings, they're going to short them together, and then they're going to measure the current. So they can't really use an ammeter, so typically they'll use some kind of CT. So they're looking for this current here. With the windings shorted, there's absolutely no load on the windings. So I of X, what they do is they use IX1, which is the field current they found from the open to produce the rated voltage with the open. They apply that same current on the excitation current, and then they measure this amp reading here. So pretty much the short circuit test says the stator phase conductor windings are shorted together, the machines are brought back up to rated speed, and the open circuit excitation current found from the open circuit test is applied to the rotor over here, and then the resulting induced current, which is going to be our I here, which is the same thing as flowing through this short, the resulting induced current in the shorted stator windings is measured and recorded. And that's either going to be I short circuit, ISC, or they're going to call that IX2. Now, what does that tell us? Well, what that does is it gives us a way to measure X of S. So say you work at a factory that builds synchronous motors and synchronous generators. How do you think they actually get this value, right? They can't just ask the machine. They actually have to do an electrical test and figure it out using math. So what that tells us is X of S are synchronous reactance. We can actually solve it two ways. We can say it's equal to E, our line to neutral value, over I short circuit. Or we can also say it's the same thing as the inverse of the short circuit ratio. So anytime you're dealing with a problem, if they give you a short circuit ratio, you know you can use that to find your synchronous reactance, right? Because 1 over X of S, so the reciprocal of X of S, equals your short circuit ratio. Okay, that's about it for this introduction. Like I said, remember, this chapter is one of those where it's just going to be extremely wordy. There's going to be a lot of definitions. A lot of the stuff's going to be new or foreign to you unless you work in the power generation industry or unless you work in the machine building industry. So don't let it get to you. Read the definitions, understand them as best as you can, but most importantly, don't let them slow you down from solving these kinds of problems. So the thing I recommend is kind of just jumping right into the problems. Make sure that you can always answer the word problems by looking things up. You don't have to be able to solve them off the top of your head. So spend time where it matters. Spend time learning how to solve questions. Hope you enjoyed this introduction on synchronous machines. For more P-exam practice problems and to try our online review course, come check us out at www.electricalpereview.com. We'll see you soon.